Welcome back to the video series on technical data sheet of coatings from a research point of view. This is part 3. In this series, I will be talking about the surface preparation and application of the coatings. Surface preparation is a really important parameter which decides not just the adhesion of the coatings but also the life and failure of the coatings. As seen here, the TDS will recommend the surface preparation for each substrate. This means that each substrate will have different surface preparation parameters and techniques. This is based majorly on the mechanical properties of that particular substrate. The substrate is prepared to a rough profile, which can be either the first one or the second one. The depth of these profiles will decide how adhesive the coating is to the substrate. If the depth is too much, then a lot of coating will be used, and even though the adhesion is more, the cost will increase. If the depth is too less, then the adhesion of the coating will not be enough. Therefore, it is important to select the perfect surface profile and hence go by the recommended standards. If you see here, the galvanized steel is told to be blasted by sweep blast cleaning. For stainless steel and carbon steel, they have talked about an abrasive blast cleaning with an angular surface profile. These two are different because in galvanized steel, we need to preserve the galvanized layer along with the surface profile that we need. If we use the blasting parameters given for carbon steel or stainless steel for galvanized steel, then there may be a chance of the loss of the galvanized layer, and this means that we will not only lose the extra protection that is there on that steel, but we will also be losing the adhesion between the upper coating and the galvanized layer. Now, in epoxy coatings, we know that there is a reaction between the resin and the hardener to get a resultant coated substrate. In a coated substrate, you have polymer chains all over the substrate made up of multiple numbers of this molecule. When you have this molecule near the substrate, that is, when you consider the part of the coating near the substrate, there is attachment of that molecule to the substrate with the help of mechanical locking. But there is also attachment of that molecule to the substrate with the help of weak attraction bonds to Fe. The attraction bonds exist between the hydroxyl group and Fe. This is because of the polarity of the hydroxyl group. Hydroxyl group has a negative polarity, and that makes it attractive to the Fe in the substrate. In the TDS, there is a section called product compatibility. In this section, they talk about the previous coat, that is, the coat that should be given on the substrate first, and then this particular epoxy coating has to be coated on top. Then there is the section of subsequent coat, which means that the phenolic novolac epoxy or silicon acrylic can be coated on top of this epoxy coating. These recommendations have been given so that there is the best possible combination if one requires to use a 2-layer or a 3-layer protective coating system. If the previous coat is inorganic zinc shop primer, then this attraction between the hydroxyl group will happen between the inorganic zinc and the OH groups. In the subsequent coat also, there will be an attractive force or a weak bond between the hydroxyl NH groups and the groups in the upper epoxy coating as well as in the silicon acrylic coating. These bonds ensure that the adhesion between the coatings is better, or they complement the mechanical locking that happens in these coating layers. Once the surface has been prepared, the coating is applied. The TDS recommends the application method. This particular coating has been recommended to be applied using an airless spray. They have also specified the nozzle tip and the pressure for this airless spray. If the pressure or the nozzle tip do not match these parameters, it is possible that either there will be less amount of coating deposited on the substrate, or the pressure will be so high that the coating is blasted off the surface rather than getting deposited. In a scientific or research point of view, when you want to use this coating or you want to improve upon this coating, I recommend you to use the surface preparation techniques and the application techniques as much as possible. In laboratories, usually it is not possible to use airless spray. Then it is recommended that at least the surface preparation method should be followed, because in laboratories usually the testing is done on roughly ground surface of metal, or sometimes they may also use 800 or 1000 grit polished surface. If such surfaces are used, the surface profiles are not as deep as required in industry. Hence, the adhesion that is measured in laboratories will not match the adhesion that is seen in industries. In fact, the failure of the coating will occur first in the laboratories rather than in the industries. Hence, it is usually better to go by the recommended standards in the TDS. Now, when an airless spray is applied, it is first necessary that the two components are mixed. In laboratories also, it is important that the mixing ratio is maintained by volume or by weight, depends on what the coating is. In this particular coating, component A to component B ratio is 6.5 to 1. This depends on density. So to check the density, we should now go to the MSDS. In the MSDS, we can see the density in the section called physical and chemical properties. Now you can see that the density for component A is different from that from component B. Even the reactions, we know that we need just one molecule of component A and one molecule of the hardener component B to get the cured coating. So why do we need a large amount of component A as compared to component B? One, this is related to the density, and two, it is related to the contents in addition to the actual resin. So if you see here, there are a lot of other contents in the component A in addition to epoxy resin, and that's why we need to have 6.5 parts to get an equivalent number of epoxy resin molecules that can react with the same number of amine hardener molecules in component B. Now, usually the packaging that is given is similar to what is required in the ratio of the coatings. So the component A is 16.3 to 2.5. So it is assumed that the hardener will be completely mixed with the resin. However, when you're researching in a laboratory, you may not use such a huge amount, so we have to measure it out properly. Hence, it is very important to see whether the ratio is given in volume or in weight. If it is given in weight and you measure it out in volume, then you will be measuring out the wrong ratio and you will not be able to get the correct coating content and the correct coating behavior. Hence, to all the researchers in coatings, please do check the ratio and use the correct ratio of the coatings only. This shelf life is really important because depending on the location temperature, the shelf life will decrease or increase. So this shelf life at 23 degrees Celsius is 24 months, but if the coating is kept in a tropical or a high temperature area, then the shelf life is going to decrease. Usually this is more important when you're doing the laboratory testing and you do not use the entire amount of coating, but it is also important when you are going to use the coating in some later time and you are going to keep those cans in storage for that amount of time. The next comes to drying and curing. So once you have applied the mixed coating, there are different times that one has to understand. In laboratories also this is really important. So here they have given a few different temperatures from 10 degrees to 100 degrees Celsius. Here there are surface dry, walk on dry, dry to overcoat, and dried and cured for surface. So the fourth part is really important. If you are talking about an area where the temperature is really low, 10 degrees Celsius, then to actually put the component into operation you have to wait for 21 days. If the temperature is really high or the component is in operation, you cannot dismantle it and it is heated to a high temperature due to the operational parameters, then the dried or cured for service parameter is just 1 day. So if it is a maintenance operation, then usually you can resume the operation, or you can assume that the coating has cured after 1 day. Now in laboratories, usually the temperature is controlled at around 23 degrees Celsius. So once you coat the surface on your samples, you will feel that they are dry to touch. When you touch it, they will feel dry after 4 hours only. However, if you want to use them and if you want to ensure that the coating has cured throughout its thickness, then you will have to wait for 7 days. I do recommend doing this to all the researchers so that you get the best possible cured coating for your further experiments, and you can simulate the conditions more appropriately to the ones present in the field. Then this will make it easier for you to translate your results to the industry. Further, these temperatures are also dependent on the conversion rates that I talked about in the first video. Please do check out the video link that I have posted here. So the conversion rates will determine how fast or slow this curing will occur. If you consider the lower temperatures, the conversion rates are lower. At high temperature, the conversion rates are higher. These conversion rates will also determine the induction time and pot life. So once you mix the coatings, you cannot keep them beyond 4 hours, because after that the coating will have reached this stage of curing, and then it will be difficult to coat it properly on the surface, because it has become tacky, and 2, it has already cured in some parts. So you're not really spreading out an uncured mixture, you are just trying to deposit a fully cured coating, and that will essentially be a major loss in the adhesion of the coating and properties as well. Now let's take the example of the city of Jaipur in India. In this city, over the number of years from January to February, there is a huge variation in temperature. So if you're coating a particular component and that component is really huge, which means that you cannot coat it in 1 day and you have to put in several days or several months, then there are 2-3 things to remember. First is the drying and curing time, and second is the flash point. So if you remember the flash point for this coating as seen in video 2, please check the link. In video 2, the flash point was 28 degrees Celsius. Now in this city, the temperature in the months of July and August goes way beyond 28 degrees Celsius. So if you choose to use this coating and coat it during the months of July or August, then the risk of the coating catching fire is really high. So one has to be careful in these particular months. Further, in the previous slide, there are these different temperatures for curing. So the temperatures of 23 and 40 degrees Celsius will be applicable for the months of July and August. So if you coat any component in these months, the curing will occur quicker than in January to June, where the temperatures are below 10 degrees Celsius. So depending on the months, you can decide whether to vary the time of curing or recoat. I do not think it is usually done, but that theoretically it is possible. That's why in research it is necessary to first maintain the temperature in laboratories to allow an even curing, and second, when you're developing a coating, you can also try and explain such curing variations in that coating so that it will be easier, or to translate your results to the industry, but it will also help you if your coating is getting cured at a lower temperature quickly. Then you have actually opened up a good field of research, because in lower temperatures the rate of curing is slow. So that is kind of a knowledge gap. If you are able to find a coating which can get cured faster at lower temperatures, then it will be a much better prospect for the industries to use your coating for maintenance as well. Now this was about the different months. If you talk about the different days also, you see that in that city there is a variation from 26 degrees Celsius and 9 degrees Celsius in just one day. Over the different days also there is a change from 9 to 14 degrees Celsius minimum. Further on there is change in the humidity also. So if you do not complete your coating in one day and you have to continue the coating process for 3 days, then the rate at which your coating gets cured will change. For example, if you begin the coating of the component in the early mornings where the temperature will be 9 degrees Celsius or around that, then at that time the coating that part of the component will get cured slowly at first. If you continue coating that component and in the morning the temperature increases to 23-26 degrees Celsius, that part will get cured faster. So now there are two regions in the same component where the coating is getting cured at different rates. This means that you have to give the maximum possible timing for curing to ensure that all the area has cured properly, or you may have to do additional testing in the laboratories first to check the most appropriate time of curing of the coating. So those researchers who are working on development of the coatings will actually benefit from trying out curing processes and curing reactions at these different temperatures and include them in their research methodology, so that an additional chemistry component is available in their research apart from the usual corrosion and adhesion testing methods also. The last point of this series is that of the heat resistance. Now heat resistance means that when you expose the coating to a dry atmosphere and if the substrate is heated up to 205 degrees Celsius, the coating will maintain its protective properties. If by some way the environment changes to wet or humid, then this temperature will not be valid and your coating may fail faster. This is related more to the mechanical properties of the coating. Now in the coating, the polymer chains are present all over the coating surface. They are essentially what make up the coat. So when you heat the coating, the polymer chains have bonds between them that will break due to the high temperature, and it will be easier for the polymer chains to move away from each other, which means that the coating may break or it will have additional voids in between, allowing additional moisture to enter the coating. Now if you compare it to a particular example of DSC, that is a differential scanning calorimetry, you can see that for different compositions of epoxy which has been reinforced with clay, you have different DSC parameters, which means that after this point, that is the TG or glass transition temperature, the behavior of the coating will change. So if you are developing coating, the components of the coating will also affect your heat resistance properties. That is why whenever you have developed a coating or you want to do a failure analysis of the coating, please go through the TDS and the MSDS and try to give the properties that are given in those parameters. Usually in research we only talk about the corrosion resistance, adhesion or chemical FTIR properties, but in TDS these are not included. TDS consists of entirely different parameters. Hence, if you want to translate your results to the industry, then please do these additional tests and try to put them in a format similar to the TDS, so that they become a ready reckoning of your newly developed coating, and it's easier for you to explain your results to the people who are working in the paint industry or coating industry. So that is all for this series. Thank you so much for checking out my videos. Do follow my channel, subscribe to it, like, share and comment, and do let me know if you need more information. I will put a video on a different topic from now on. So if you feel you have any information that you need and you would like me to make a video on that information, please comment or get in touch with me through LinkedIn or YouTube, and I will try to make a video on that particular topic. Thank you so much. See you.